Hi, my name is Zachary Diggins, and today I'll be presenting to you about the impact of gamma radiation on range-finding sensor performance. I'll be presenting on behalf of my co-authors, Mahadevan, Herbison, Barth, and Witulski from the electrical and engineering departments of Vanderbilt University. Before I begin, I'd like to thank our sponsor for this work, the Defense Threat Reduction Agency. So, what do rangefinders and gamma radiation have to do together? Well, one place where they would likely to encounter each other and where they'd be useful, rangefinders would be useful, is the mitigation of radiation accidents. Unfortunately, when radiation accidents do occur, you need to do work in a high radiation field. It's very unsuitable to send humans into this environment due to the health risk involved. Humans do not survive well in radiation environments. Unfortunately, robotics and CMOS electronics and other types of electronics also suffer degradation in these radiation environments if the fields and length of time are high enough. So an important task is figuring out how to use these robotics or these types of sensors in these environments and use them reliably and use them for long enough time to do useful work. On the picture on the right here, this is a photo from inside Fukushima taken from a robot doing surveying after the disaster, looking to explore the environment. And what we see here is a highly unstructured environment, something where your maps and your previous plans of how you would route may be gone, may be changed. You see a lot of debris, a lot of different things. And in this environment, there may be a variable radiation field, different types of radiation that damage your robot as it's trying to do its task in this environment. So what we're going to look at this, what I'm going to demonstrate in this work is how rangefinders degrade and how this can lead to loss of environmental awareness in these types of applications. So to go into a little bit more detail, what we see is an environment where you have radiation, this can lead to defects and damages in your electronics and in your sensors. This can lead to parameter shifts in these sensors. So for example, if you have an amplifier or something, you could have a threshold voltage shift, you could have increased leakage current, you could have changes in your sensor characteristics. This ultimately propagates upwards to a certain level effect and leads to overall sensor degradation. It's important to note here that we're not just talking about a sensor giving out perfect information or failing. There could be some sort of parametric degradation along the life of the operation. So I want to demonstrate that here. In the ideal case, when you have a sensor, this is the physical quantity you're interested in measuring, and your sensor will give you out some measure of that physical quantity. And there will be some mapping. Here I have a 1/x, for example. And what you do is you record this in the lab, you understand this about your sensor, and when you deployed your sensor in the field, you would have a lookup table where you looked up that threshold voltage, so that voltage that you sent from your sensor now and exactly determine the physical quantity. So what can happen in a radiation environment is you can have a shift in this relationship due to parameter changes in the sensor. So instead of having this curve that you had before, now you have some different mapping between the physical quantity and the measurement of the sensor output. So what this does is it leads you to a different lookup value, but you're still using the same relationship that you mapped previously, which leads to an inaccuracy in the measurement that you're making. And depending on how inaccurate this is, and depending on the situation that you're in, this could have consequences in your ability to make good decisions and to perform the task that you're trying to perform. So it's important to note here that this shape, I showed it here as a shift downward, but going into this work, depending on the type of sensor, it could be various shifts. You can have it turn in shape, you can have it go up or down, all kinds of different things. So that's the effect that we're interested in capturing here. Not just when it breaks, but how it gives you bad information before it breaks. So to measure this curve for the sensors that we did, with a variety of rangefinder sensors, I'm going to go into more detail about what they are later, but I just want to demonstrate the experimental procedure for now. And we had a fixed sensor mount and a movable target. And over a range of about 2 meters, we would move this target and plot out the input-output mapping of the sensor. The mount was accurate, and we made sure of this so that any changes and variations we see were due to actual changes in the characteristics of the sensor and not of the mounting or positioning. So just to animate here, you move the target, get your next point, move your target, get your next point. And we would do this more than 3 times. We would do this several times to map out this curve. So once that was done like you would do if you were going to deploy a sensor. You would do that once and then send your sensor out in the field or whenever you wanted to recalibrate. But what we would do is we would take that curve and then we would expose the sensor to a known radiation dose, the total ionizing dose, using a cesium-137 irradiator. This emits gamma radiation around 660 kiloelectron volts. We would then take a step of radiation. We would take the sensor out of the irradiator. We would generate this curve again, and then we would repeat this process. So then what you end up with is a bunch of 3D mappings where you have this same curve here where you have the actual physical distance and the sensor output. And then you can imagine what I'm about to show you is a third axis where you have dose as time increases, as the number of steps increases. So here, I'm going to show all the results at once just so you have an idea of what's coming, and then I'm going to go into detail later. So don't try to take in everything off this slide. There's a lot of information here. We looked at 3 different sensors. This is a IR sensor, an infrared sensor that uses triangulation. It has an IR LED and then a lens receiver, a diode receiver. This is a sonar that uses time of flight to make its measurements, outputs of 40 kilohertz ultrasonic pulse, and then looks for the echo. And the sensor here is a laser rangefinder, which generates a laser spot and has a CMOS camera array that looks for this position in the column of the spot in the array, and as you move closer and farther, that position changes. So what we see here is that as we increase the dose, the function of these different ones degrades, and it degrades differently. So now I'm going to go into the details of the 3 sensors and talk about why we see these effects. And what it comes down to is the differences in the sensor architecture leads to the different types of response. So the first sensor I'll talk about is the laser rangefinder. I have a picture of it here. As you can see again, just to remind you, it has a laser here, the camera here, and then detects the spot. And as you move closer and farther away, the spot changes. The sensor was the most digital of all the sensors we looked at. It had a camera, so it was detecting a column, it was detecting a pixel, it was detecting a number there, and it was had a lot of built-in interior microcontroller that was doing the processing. So what we saw with this sensor was no degradation at all. It had the same transfer function, the same mapping, the same relationship here. We have this is the axis I showed you before, and then now I've added this dose axis. So as you increase in dose, you come this way. So here's the first curve, here's your next curve, and then the device failed. It stopped responding to it stopped giving it serial communication output. So this is one type of failure you can observe. If you have a highly digital sensor with a lot of supporting electronics, if one of those components goes, we measured a lot of test points, and it turned out that it was the microcontroller was the first element to fail in this case. You'll have this cliff-like behavior. This has interesting implications. This was the first sensor to fail in terms of dose, so it had the lowest survivable dose. But the nice thing about this sensor is it either gave you good information or it failed. It didn't babble, didn't give you bad information that you could potentially make bad decisions off of at any point. So this is the first sensor here. Next, I'm going to show the degradation for the sonar that we tested. We have the same axis, same type of curve here, where we have distance and sensor output, and this is the pre-rad curve here. And then as you increase the radiation, initially there's no degradation, and then we see some changes at the far distances. And then finally we enter kind of an unstable region where the sensor is giving out basically nonsense throughout its range, and then we see a complete sensor failure at this dose, around 18 kilorad, as I would do. The characteristics of this degradation are caused by the way this sensor system was designed. What we see here is these long distance changes occur due to changes in a charge pump that's on the circuit. The voltage that the charge put was supposed to output was plus 5 volts to negative 5 volts. As the irradiation increased, this drifted downwards to 4.5 to negative 4.5, 4.2 to negative 4.2. And that affects the power that the ultrasonic transmitter is outputting. And that led to different characteristics in our far range sensing. And then here, when we enter this unstable region, it's again bad behavior in the microcontroller. The device is degraded, so it's not operating stably. And this kind of region has interesting implications because it did not give any indication to the user that the device was behaving poorly. So we knew because we knew the actual distance. But if you were operating this device, if you were using it in the field, you wouldn't know what the actual distance was. So if you were given this value here from your sensor, a value in time of 1,000 microseconds, you wouldn't know whether that was an actual 1,000 microseconds and your sensor was healthy, or that your sensor was actually in this degraded, unpredictable state. So that has important implications here, because this sensor actually feeds bad information upstream into the system. And then we saw complete failure and failure to respond at high enough dose levels. So for the third sensor, this one was interesting. This was the IR sensor that I showed you before. This was the most analog of the other sensors by far. The other two I showed you previously had a lot of system architecture built around the sensor with the microcontrollers and whatnot. This sensor here had a much more analog style interface. You have the LED here and a position sensitive detector. So the LED outputs infrared light, and then where that light is focused on the position sensitive detector will produce a different voltage in the signal processing circuit. And then you have an output circuit here. And this whole device was on one die, so it wasn't separate components, it was one integrated die. Because of the integrated and more analog nature of this, we see very interesting characteristics in the shape of the mapping from the input to the output as we increase dose. So here again you have your sensor output and your distance, and this is your pre-rad curve right here. And what we see as we increase dose, we see this non-monotonic shift in how the sensor operates. And so we see it kind of goes down and shifts down, and then shifts back up, and then goes back down. And this is very interesting. And the effect of this, the cause of this shape of behavior is the interactions and changes between these different circuits. As your voltage regulator degrades, at the same time your signal processing circuitry is shifting, at the same time your drive circuitry and your position sensor detector, as all these parameters are interacting, and as they're all degrading, the combination of those effects produces this interesting shape. There's an important implication to this shape, which is that just because of its irregularity and because of its non-monoticity, it's really hard to track just the total ionizing dose and then recalibrate. So you could think about, oh, I know I'm going to put this into a radiation environment, so I'm going to measure a bunch of steps in radiation, and I'll recalibrate my system as I go. But what happened is we saw this shape for one device. We tested several of these devices, and each one had these different peaks and valleys and upshifts and downshifts at different points for the sensor due to mismatches and fabrication tolerances within the device. So this makes it very challenging to track and know the transfer function curve. One other point I'd like to make on the slide is that if you look at the dose axis here, we're all the way up to 90 kilorad SiO2, which is over 10 times what we saw for the first sensor. So even though we're outputting harder to use information and less accurate information, the sensor survives for significantly longer. Okay, so just to compare these outputs very quickly, you can see here's the laser rangefinder, very digital system, fails abruptly at low doses. You see the Sonar, which is still a highly digital system, has some degradation, some unpredictable behavior, and then fails at slightly higher dose. And then you have this highly analog system, which shows a lot of non-monoticity, but then fails at a much higher dose. So one last point, we saw an interesting correlation between supply current of the different sensors and the dose. So this provides a potential opportunity to do some kind of mapping between, or some kind of detection here. If you see, this corresponds to when the Sonar was a regulator and when it failed, and this corresponds to when the laser sensor failed. So from a systems level perspective, if you measure these parameters that correlate to your degradation, you can make decisions and possibly think in the future about some kind of sensor fusion or what sensors you want to trust at what points during the operation. So I'm just about out of time, but to conclude, we observed abrupt failure and degradation in the input-output mappings of these sensors. The supporting electronics really are what dominated here. So it wasn't the piezoelectric Sonar transmitter or anything that was dominating the degradation. It was really the supporting microcontroller and other digital elements. And there's a potential, so we could redesign these sensors if we had an understanding of that. And there's a potential here to use sensor health status indicators for the higher system level to use the sensor to better effect. So that's it.